Okay, welcome everybody to episode 13 of Games with Go. Today we're going to start turning this balloon thing into a little bit of a game. Um, if you've ever seen iPod games for little kids, there's one where balloons float around the screen. You can touch them to pop them. Little kids love it. So we're going to do something along those lines. And one of the things we'll need to do is have a way to move our balloons around. We're going to try and bounce them around the screen. And one nice way to do that is to start building up a vector library. This is something that game frameworks and engines almost always provide is a vector library. And we're going to start building up our own that we can use in this game and others that we work on later. So what is a vector? So a vector is a direction and a magnitude or length. So you could think of them as an arrow. So the direction would be which way it points, and then the length would be how long it is, say 5 units. Vectors can have different operations you can do on them. For instance, you could add vectors. So you could take this vector and this vector and make this flat. And you could add them. And you can add them visually by sticking one on the end of the other. So that would be the first vector, the second vector. So the line connecting would be the result of adding those two vectors. You can also multiply vectors. So if you had a vector pointing, say, this way, with a length of, say, 2 units, you could multiply that by some number, like 2. And that just makes a new vector that goes in the same direction. That would be twice as long. So that would be 4. Another common operation on vectors is to normalize them. So say you've got some vector, could be any number of units long, we'll call it n. And if you normalize it, you get a new vector pointing in the same direction that is 1 unit long. And that's often useful if you want to resize a vector. You can just normalize it and then multiply it by a number to get a vector of a certain size in the same direction. Okay, now vectors could be represented a couple different ways. You could represent it by an angle and a length, right? That would be one way to do it. But the way it's done usually in games and graphics is not that way. It's usually done with an X and a Y. So the X would represent, for instance, if this was our vector, the X would represent how far along the X-axis it goes that way, and how far along the Y-axis it goes that way. And then if you want to, you can compute the length and the angle from that X and Y. So the reason that is one reason that's a nice way to represent it is you can use the same structure, an X and a Y, to represent a point, so like a pixel. So if you had some object that you were drawing at a certain point, x, y, and your object had a velocity, which was represented by another vector, say something like that. Say it's 2 units per frame in that direction. Then to move your object, you can take your vector that is representing its location and add the vector representing its velocity, and the result will be a new point where your object would be. Okay? So that is the basics, and let's start let's start building a little vector library. So let's open up VS Code, and we'll make a new folder for this, because this will be something that we can use in lots of projects, not just for this one. And we'll call it vector3, or sorry, let's call it vec3. Go package names are supposed to be short, so we'll make it short. Make a new file, vec3.go. We'll call the package vec3. So we're going to use a chat is talking about physics and linear algebra 101, and that's absolutely right. This is linear algebra in disguise as something fun. It is a good idea to find a good linear algebra book if you're interested in doing 3D programming, especially because it's unavoidable. Okay. So the first thing we want is simple. We're going to want a struct for our vector3. And that's going to have an x and a y and a z. And we're going to do we'll do 32-bit vector 3s. You'll notice I'm capitalizing these because we want to export all of these things. They should all be publicly visible to other programs using this package. Okay, so functions we're going to want to make available. We'll want to do an add. And there's a couple different approaches to designing an API like this. You could use receiver values. Right, you could do something like this. And you provide a second vector here and then return one. But we're not going to do that. We're just going to do it like this. We're going to do, you provide the two vectors you want to add, and you get back a new vector. So adding vectors is really simple. You just add up the components. So this would just be a.x plus b.x. and a.z plus b.z. Wrong symbol. All right, we're going to want multiply, and you multiply a vector by a number, not by another vector. But the result is a vector. And this is also simple. A.x times b, b.x times a.y times b, a.z times b. Piece of cake. A function to get the length of a vector. And I guess this should probably be, this definitely makes sense to be a receiver. So we could do this like this. And you'll notice here I'm not using a pointer like I have in the past. That's because we know vectors are always just going to be 3 float 32s. It's not a lot to copy. It can be advantageous just to leave it as a value type. So here we need to do, let's call this just v, or let's call it a to be consistent. So we take a.x times a.x plus a.y times a.y plus a.z times a.z. This may look familiar to you. Then we'll use the math library, so we need to import that. To get square root. And we'll need to cast this to a float 64 and then back to a float 32. All right. So now we've got length. Distance. So if we're treating two vectors as points, we might want to know the distance between them. And to do that, we want to get the difference between each component. Call this xdiff. And if anyone sees me make a mistake, yell at me in chat. Then we do the same equation as for length. All right, another one that can be handy is distance squared. So the reason for that is square root's kind of an expensive operation. And sometimes you just need to know if one thing is closer to something than another. And so the square root doesn't matter, right? You just want to know if one thing is closer to a than another thing. You can skip the square root, save yourself some cycles. Finally, normalize. So we'll take in a vector 3, return a new vector 3 that's normalized. And first step is to get the length. So we already have a function for that. And then we just divide. And that'll give us a normalized vector. All right. And that's going to be it for our vector library. So let's go back to Balloons 2. And first thing, we're going to, someone's asking, what is a normalized vector? So a normalized vector, if you start with some, I can't draw. There we go. Let's erase. A normalized vector just resizes it to a size of one unit. So if this were a vector of 5 and you normalize it, you get a new vector in the same direction but length 1. That's all. And it's often useful if you just want to know what direction something is, you might normalize it. If you want to resize a vector from 5 to 10, you can, or say you have a bunch of vectors incoming of various sizes. You want to resize them all to 10. You can just normalize them all, and then you can multiply by 10, and you'll get a bunch of vectors, same direction at 10. All right. So first thing, small bug fix. The very bottom, if the elapsed time is too quick, this should be times 1,000. And that will be important because we're going to use this to move our balloons around. Okay, then up to load balloons. So currently, we're just loading up our 3 textures and making 3 balloons out of them. We want to be able to make like thousands of balloons. And we don't want to make thousands of copies of each texture. We only want to have 3 textures, 1 for each color, and the thousands of balloons can all share the same texture data. So we don't have to load the textures multiple times into memory. So we will change this. Well, first of all, we're going to end up returning an array of pointers to balloons. So change that. And then, so here we're going to change this. Our first step will just be to make the balloon textures. So let's rename this to balloon textures. And this will be an array of STL textures. So we'll do all the same stuff up until this point. We're not going to make a balloon out of it. So we're just going to say balloon textures of I equals texture. balloon textures. And we're going to move this out. And then we'll have a parameter here where we take in how many balloons we want to make, called numBalloons. Then we need to make a balloon array, numBalloons big. Balloons equal to. Then for I balloons, range balloons. So we'll want to get, let's get an even split of textures. So we can do that by saying the texture is equal to the balloon textures of I mod 3. So the mod or remainder operator, once it gets to, it'll go 0, 1, 2, 0, 1, 2, 0, 1, 2. So we'll just keep getting the same textures over and over. Then we can say balloons of I gets the texture. So our position, we were just using as a function of I before. That's not going to work anymore now that we have thousands of balloons. So let's make some random positions. So for random, we're going to need the math library. So let's import that. And let's see. Yeah, so, balloon's not going to have position anymore. So previously we had this position struct. We're going to kill it because we're going to use our vectors now. And we can't just embed the position or the vector 3 type because we're going to have two vector 3s. We're going to have a position and a direction. So this will be where the balloon is, and this will be how fast and in what direction it's moving. And we'll need to import vec3. Oh, so here's a tip. It's not always recommended to do this, but since it's our own library, I'm pretty comfortable with it. If you put a dot before your import, you don't have to type the package name to get at it. Downside to that is you could have name collisions if the thing you're importing uses the same names as you. That's why they don't recommend it. That's why it gets underlined in green. But I'm going to do it. I'm going to live dangerously. Okay. So this will need to become balloon.position, or sorry, position.x now, position.y. Oh, capital X, capital Y. Okay. So let's put each balloon at a random position. So we'll get what is the, do we need math/random? Yep, math/rand. There we go. Okay, we'll get a float 32. So we'll make x from 0 to the window width. So float 32 returns a number between 0 and 1. So we can multiply to make that between 0 and the window width. And window height. And then we're going to add a new thing. We'll make a window depth. Start out at 100, see how it goes. All right, we also need a random direction. So we'll start out with no idea yet how fast these should be going. Don't need to do this. And that needs the address of a balloon, I think. Width and height undefined. Okay, so we could just assume all the textures are going to be the same width and height, but let's be safer than that. What's the proper way? Yeah. So you can ask SDL how wide and tall a texture is. There's a function called text.query. You'll see it returns a bunch of things. It has 1, 2, 3, 4, 5 return values. So I'll just show the documentation for this real quick. So the things you get back are the format, the access setting, and the width and the height. And you also get back an error potentially. So all we want are the width and height. So what we could do is we can say underscore because we don't care, underscore we don't care, width, height, error, text.query. We will check the error. And now we have a width and height. And we just need to make them, I think these are int32s. Make them ints. What are we forgetting here? Oh, scale. We're not going to need scale anymore. So let's delete that. We'll come back to this in a second. Okay. This looks happy now. All right, cool. We now have a load balloons that will give us a whole bunch of balloons back at random positions and moving in random directions. Okay. Delete that comment. Another thing we can get rid of, this we're not using anymore. So delete that. That was when we were rendering to a single texture when we were doing everything in software. All right, let's start with 100 balloons. And let's get rid of this direction flag because we're going to do real balloon moving around instead of this. Okay. Now let's go up to this. New width and height. So we need a scale. And we're going to do sort of a pseudo 3D effect by just making the balloon smaller or bigger based on how far it is away from the screen. So we'll say that scale is equal to, let's see, we have our depth, and we'll say, if we do 200, be 0.5, be 0. Oh, the depth is the z value. Position.z. All right, we'll try that to start out. That gives us a scale. Let me draw. So let's see if we can run this. All right, got a bunch of balloons. That is awesome. All right, so let's start moving them around. So kind of like we did with Pong, we're going to have an update function for our balloons. And that will need to take a elapsed time so that we do not depend on the frame rate being constant to do the right thing. And now we're going to use our vectors, some of our vector functions, to move this balloon around. So what I'm going to do is I'm going to get a possible position for the balloon the next time it moves by adding the balloon's position and the balloon's direction. But remember, we need to use the elapsed time to affect how far it moves. So we will multiply the balloon direction times the elapsed time. All right, then we wanted to check if the balloon has hit the edge of the screen, whether it's hit the left, right, top, down. Someone is asking about how we're doing the depth. 1 over depth. It just depends if you want to treat 0 as the front of the screen or 0 as the back of the screen. We'll see what it looks like. It might be better to switch it around. It gets tricky if you let the balloon get to size 0. It looks kind of wonky, so we're going to want to avoid that. Okay, so we want to check to see if the thing hits any of the boundaries of the screen, which is just your basic grunt work. Okay, so if it hits the edge on the x-axis, all you want to do is reverse the x component of its direction. Right, real simple. Then we'll do the same for y and z. And then we will actually change the balloon's position. And the reason we're doing it this way, where we get like kind of a temporary position and check it and then actually set it, is so that the balloons don't get like stuck onto the boundary, which can happen sometimes with with floating point, right? Like you hit the boundary a little bit beyond, you change the direction, but you're still beyond the boundary, so you change the direction again, and the balloon just starts kind of wiggling. So that'll prevent that. Okay. Let's try elapsed time. Okay, so we need to declare elapsed time outside the loop. That'll be 0 the first time. Okay, they're moving. Moving too fast. Slow it down. So let's go. Where were we setting our speeds? Maybe this should just be between 0 and 1 after all. All right, that's better. We can see it moving in and out of the screen too. Okay, so one thing you might notice, since all our balloons are the same size, we should never see a smaller balloon on top of a bigger balloon, because a smaller balloon is one that is further behind. So it should never be on top. So how do we do that? We need to sort our balloons by their Z position. And to do that, Go has a built-in sort function, but we have to do something to use it, which is we have to satisfy the sort interface. So let me pull up the documentation for that. Let's see. Where do they define the sort interface? Well, maybe they don't show it in here. So I will show you. So in order for Go to sort something, it needs to know 3 things. It needs to know how long your collection of things is. It needs to know how to swap things from, it gives you 2 indexes and it wants to know how to swap them. And it needs to know if one thing is less than another thing. All right, len, swap, and less. And if Go's sorting algorithm can do that to your collection of things, it can sort your collection of things. So to do that, we use a Go feature called interfaces. So an interface is a contract, right? So if we say, we can make our own interfaces too. So if we made one, like this, it would mean that any struct you make or any type you make that has an add receiver type with this form can be an addable, can be considered or treated like an addable type. So when you sort something, it needs to satisfy the sort interface, right? It needs to satisfy that contract. And if it provides those methods, then sort can work with it because it knows it can call those 3 functions we showed earlier on your type. It doesn't care what your type is. Your type could be an array, a linked list, a tree, whatever you want. As long as you expose these methods, the Go sort can sort it. All right, so we need to expose these three methods on our array of balloon pointers. So first step to do that is you can't directly make a function that uses an array of pointers as a receiver type. Go just doesn't allow that. All right, it's going to complain invalid receiver type. So you got to give it a name. So this is just a type alias. Okay, it means we've made a new type called balloon array, and that type is just an array of pointers to balloons. And that lets us make a receiver function to it. All right, and len has to return an integer. So this is simple because we can just return the length of the array. Let's call this balloons to be good. Okay. Then we need swap. So swap, we're going to be given 2 indexes into our collection of things, and it's our job to swap them. So you can use Go's kind of multiple return syntax to do that in one line, which is kind of neat. So you can say balloons I and balloons j is going to equal balloons j and balloons I. So that'll take the ith element of balloons and the jth elements of balloon and swap them. Last thing we need is less, which takes 2 indexes again and returns true or false. All right, so that's simple. We just return whether balloons of I is less than balloons of j, except we want to compare only the z value of the position, because we're going to be doing z sorting. Okay, so now we have balloon array, which can be sorted by Go's built-in sort. We'll need to bring in the sort package. So now we should be able to say, let's see, how do we call it? So we can say sort, and then we pass it our balloon array. And that should be it. Now the other thing we want to do is we need to do the update before we do the sort, because we don't want to sort them and then move them again, because the sorting could change. So we'll take this loop here, update in one loop, draw in the other, and sort in between. So let's see what that looks like. All right, that's kind of busy. So let's do a few things. Where are we doing our scale? Let's make the balloons a little smaller, and let's move them a little slower so we can see what's going on. Let's make fewer balloons too. All right, now we can see that the small balloons go behind the big balloons. That is good. So there are some problems here though, and you might notice that like sometimes the balloons kind of flicker back and forth a few times. Like one will go, oop. Tangent asks, what if you want to sort on either position X or position Y? If you wanted to be able to sort on different things, you would just have to make multiple type aliases. So, right, you could make a type balloon array Z and a type balloon array X, and you'd implement these functions differently for each one. That's how you do it. Or write your own sort function, then you can do whatever you want. Okay, so the problem we have here, which is, it looks minor, but it could be worse if we were moving the balloons at different rates. Sometimes like they'll kind of flicker back and forth a few times. And that's because we talked about before how floating point math is not exact. And so if two balloons are like moving at similar speeds, the Z positions could flip-flop, flip-flop, flip-flop. So there's two things we need to do to fix that. First is sorting. There's two kinds of sorts. One kind is a stable sort, and another is an unstable sort. So what does that mean? So say we had balloons A, B, C, and D, and that their Z positions were, say, 2, 1, 1, 4. A stable sort will guarantee that even though B and C have the same Z value, that they'll stay in the same order. So it means when it gets sorted, the result will be B, C, A, D. Right? Whenever they're the same, a stable sort will preserve that order. An unstable sort does not guarantee that. It might end up this way, but it might also end up that way and swap it. So you can see how that could be a problem, because if two balloons are at the same Z value, the sort running over and over could keep switching them back and forth, back and forth, back and forth. And we don't want to do that. We want to keep it the same so it's not flickering around. So Go has a stable sort built in. So that's one thing we need to do. And the downside of a stable sort is it is usually a little bit slower. If you're free to not worry about the order, you can make your sort a little faster. So the stable sort will be a little bit slower, but prevents us from the flip-flopping. The other thing we can do, because we can still get some flip-flopping just because the floating point values can keep subtly changing and putting one in front of the other, is we can make this less function, less sensitive to small changes. So what we could do is only report if it's less, if it's quite a bit less. So we could do something like balloons. Right, so now it's going to be like less likely to switch positions until one balloon is quite a bit behind another. So let's see if we can even see that difference at all. Yeah, it's hard to see the difference with the balloons moving at these rates, but I have seen it flicker worse before. Tangent asks, isn't the flickering just one balloon moving in front of the other? And Yes, like you do expect that. As one balloon moves in front of the other, it's going to pop in front because we're not bouncing the balloons off of each other. But what can happen is it can flicker back and forth a bunch of times. Like say if two balloons are like moving kind of near each other, they can go back, forth, back, forth, back, forth real fast, which you don't want to see. It's called Z fighting. It's also a problem that comes up in 3D all the time. And in 3D, there's other ways of dealing with it. Okay. So we've got balloons bouncing around pretty well. We can draw tons of them. So that's good. But now we want to start doing mouse input, I guess. That would be next. So we want to be able to do mouse and touch inputs so that we could click on a balloon and pop it. Right, we've done keyboard and joystick input, but not mouse input yet. And I kind of intentionally didn't fully sort this out ahead of time so you can kind of see how one goes about learning an API when you don't know anything yet. So how do we get the mouse state in SDL? This is the SDL2 docs, and you can see there's a function, get mouse state. And so you can get back the Y position and X position, and you also get back a 32-bit button bit mask of the current button state. So if you're not familiar with bit masks, they're kind of a way to squeeze a bunch of data into a small space. So like a single 32-bit integer can contain data about 3 or 4 different mouse buttons at one time. And you can do bitwise operations on those masks to extract the things you want to know about. Like right here, they get the mouse state, which returns a 32-bit int. This is a bitwise AND. So the result of that will either be true or false for the left button being pressed. And this is a common thing you'll see in C. It's tricky in other languages because they don't let you treat a 32-bit integer as a Boolean. Like they won't even let you cast a 32-bit int to a Boolean. So we'll have to write some code to deal with this. So let's make our own buttons or mouse state structure. And we'll want to know about the left button pressed or not, right button pressed or not, and then X and Y, which will be integers. I think that's all we'll want to know about. There's also a mouse wheel and center mouse button, but I think we will not want those right now. And so we're going to need to figure out how to take that 32-bit integer and do the bit masks and stuff to set these things up. So let's give it a go. So in here somewhere, let's call sdl.getMouseState. Let's see what that gives us back. So we're going to get back multiple return values. We get back an X and a Y and the state. So let's just start out by printing those, see what they look like. All right. So you can see if I'm not pressing any button, the third value there is 0. If I click the left button, I get a 1. Click the right button, I get a 4. Click both buttons, I get a 5. All right, and that's because the least significant bit is being set if you press the right button, and 2 bits up from that is being set for the right button. When you combine that, you get 4 plus 1 is 5. All right, so let's extract that information. So we can do that bitwise and. Is that what that's for? Let's try that. Okay, that comes back with a 1. See if it works for the right button too. Left gives us a 1, right gives us a 4. So I want to be sure I understand what this is doing. Okay. So this will work. So what we want to do is we will make a mouse state. And we'll set x equal to mouse x, y equals mouse y, and so if the left button equals 0, then the left button is not being pressed. So I think we can do that like this. All right, now this is a big mess, so let's just make this a function. Where should we put this? Let's put it under our mouse state function. Get mouse state returns a mouse state. We'll just move this all up into here. Let's rename that. So Control H I'm going to call it result. and we'll return it. All right. Now, a common pattern you'll notice when you use low-level input libraries like this, it comes up in other frameworks too, is you'll often want the previous state of the mouse and the previous state of the keyboard, as well as the current state. And the reason for that is, let's say that there was, a bunch of balloons. Let's go back to 100. A bunch of balloons. If someone left clicks, if all you're checking to see is if the left button is pressed, then you're going to pop like 900 balloons per second, right? Because every frame you're going to pop another balloon because the left button has been held down. So what you might want to do is detect when someone has pressed and then released the left mouse button. So to do that, you need to know if the button was pressed the previous frame, and then if it's not pressed on this frame. That lets you know it's just been released, and you can count that as a click. So if you want to have that option, same for keystrokes, if you want to know if it's been pressed and released, you need the previous state and the current state. So what you can do is get the current state. At the start of your frame. And let's actually declare these up here. Current mouse state. Oh, we don't need that. Okay, so we'll keep getting that every frame. Then at the end of our frame, we don't need that there. We'll set the previous mouse state equals current mouse state. Okay, we're not actually using it anywhere yet, so it's upset. So what we can do here is we can say if current mouse state dot left button, if that's not pressed, and previous mouse state dot left button is pressed. Let's just see if that behaves like we want. We'll call that a left click. See if it works. Oh, we got too much print lining to see what's happening. All right, so if I press and hold nothing, when I let go, I get the left click. So that's the behavior we're looking for. Thank you to, I can't pronounce your name, Kosche for subscribing. By the way, you can, if you have an Amazon Prime account, you can use it to subscribe for free to one channel on Twitch. And if you do that, you don't have to watch ads when you start the stream up. All right, it has been an hour, and we've got the basics of mouse input working. I think we'll stop there, and we'll continue with the mouse stuff tomorrow and start making balloons disappear. And we'll also get touch input working. I won't be able to demonstrate it on stream because my stream PC doesn't have a touchscreen, but it's something maybe you guys can test if you have one. Any questions about anything so far today or from previous streams? So last time someone had a question about whether STL was using OpenGL when we do the accelerated rendering. And someone mentioned a way to check that. So what you can do is you can set SDL to a verbose log priority. So you can do SDL.log set all priority, log priority verbose. And if you do that, and then run your program. Oh, wait, it's not doing it. So another step. There we go. It'll spit this out at the beginning. It'll say info created render direct3D. So on my system, because I'm on Windows, it picks that because that is what it believes will be the best performing, most reliable renderer. If you are on Linux, this would almost certainly be OpenGL. Or if you do a software renderer, which you can do by setting this, you'll see it'll just say software, or SDL is doing it by itself. So the Maribee says plans for handling balloon collisions. Yeah, so one thing we could do to make it look a little nicer is have the balloons bounce off each other. Doing that really precisely would be hard, but we can just sort of treat them as rectangles and make them bounce off each other. I don't know if we're going to do that or not. We might. It would make it look a little nicer if they weren't kind of popping in front of each other. If instead they bounced off each other. If they collided, that can make things look better. So maybe we'll do that. And if you just treat them as like boxes, then doing the collision detection is pretty easy. So maybe we'll give that a try at some point. Anything else? So the other things we have planned for next episode is playing some sounds and starting on doing animations. So we're going to make these balloons have some fiery explosions because that'll be fun. All right, that's it for tonight, everybody. Thank you for tuning in, and I'll see everyone Thursday. Good night.